Okay, so my name is Stephen New, and I'm in the Pure Math department, and I teach lots of assorted courses. And I've chosen today to talk about some spherical geometry, which is not normally taught in any of our courses, none of our core courses anyway, but it's a topic that you can add to a lot of different courses. So for example, you could add some spherical geometry after a calculus course when you've done some integration. You can add some in a linear algebra course after you've talked about cross product. And in 15 minutes, I'll probably just talk about a few aspects of spherical geometry that you could do after doing some integration. I usually teach on the blackboard, so I'll do that. I don't usually use overheads. The first topic is about surface area. So after you've talked about, say, arc length or surface area, after you've talked about arc length, you can talk about surface area and come up with a formula for calculating the surface area of a surface of revolution. Say if you have a function y equals f of x, and you take its graph between a and b, and then you revolve that graph around the x-axis to form a surface, then you can calculate the surface area. And let's suppose we've already done that, but here's just a quick review of how you'd calculate surface area. First of all, to calculate arc length, you imagine cutting your curve into many small segments, and then you approximate the length by a sum of straight line segments. And this segment, I could call it dl or delta L for a small piece of length, and that would be given by square root dx squared plus dy squared, or you might write delta x squared plus delta y squared. And you could write this as the square root of 1 plus dy over dx squared dx. And then you can treat it as a Riemann sum, and the total length is approximated by a sum of these, and the actual length is the integral from a to b of dl, which I'd write as the integral of 1 plus dy dx squared dx from a to b. That's your length. Okay, a formula giving the length. And if you wanted a formula giving the surface area of the surface of revolution, then you can imagine taking that line segment and revolving it to form a little piece of a cone, and use the area of the cone, or you could approximate the area by imagining that it's got the same area as a cylinder of radius y equals your function of x. And a little piece of surface area is given by 2 pi y, which would be the circumference of a central circle along that piece of a cone, multiplied by dl, or 2 pi f of x square root 1 plus dy dx squared dx, and that gives you a formula for the area. And in particular, you can use that formula to calculate a formula which is related to the area of the surface of a sphere. So if you have a sphere of radius r, which is given by y equals square root r squared minus x squared, and if you want to calculate the surface area of a portion of that sphere, a portion that lives between two planes, say the plane x equals a and x equals b, if that's the x-axis, there's two planes that cut that sphere. And if you wanted to find the surface area of the portion of the sphere that lies between those two planes, then you can get it from this formula that presumably has been done in class, and that surface area would be the integral with x going from a to b of 2 pi times y, which is this square root, multiplied by dl, which is given by that formula. In this particular case, it's the square root of 1 plus, and then you take the derivative of that, which would be negative x over the square root r squared minus x squared, all squared dx. Okay, this we can simplify. Okay, so simplify that. There's an r squared minus x squared. If we simplify it, then we'll have an r squared minus x squared plus x squared. And it simplifies to r squared over r squared minus x squared. And then the square root of r squared minus x squared cancels, leaving the integral of 2 pi r dx with x going from a to b, giving a very simple final answer, 2 pi r b minus a, or if you prefer, 2 pi r delta x. Okay, so you go through that calculation. This is actually sometimes a surprising result because it tells you that the surface area of the portion of the sphere between two planes only depends on the separation between the two planes. It doesn't depend on the position. So if you slice it with two planes near the equatorial circle, or if you slice it with two planes over here near the pole, okay, then the area only depends on the separation between the two planes. And that's a slightly surprising result, but it's a well-known result in spherical geometry. Okay, it doesn't depend on the position of the slice, it only depends on the thickness of the slice. In particular, if you consider a slice of thickness 2r, you slice it with two planes at the two poles, then you get the entire surface area of the sphere. And that's a well-known formula that students usually know from high school. So if you take delta x to be twice the radius, then you get the entire area of the sphere being 2 pi r multiplied by 2r, or 4 pi r squared. That's the area of the entire sphere. Okay, a lot of students know that from high school, and then they can see it again using some calculus. Let's do a few other formulas. So let me get another formula. Suppose we're interested in a circle on the sphere. Okay, imagine a circle on the sphere. You could call it a spherical circle. A circle on the sphere is the set of all points which are equidistant from a given point on the sphere. Take a point on the sphere, travel along the sphere through a fixed distance, say r for radius, the radius of my circle. I can form a circle on the sphere of spherical radius little r, and I've got a big R for my radius of the big sphere. So we can talk about a spherical circle, a circle on the sphere. It's also the same thing as the intersection of a plane with the sphere. Okay, when a plane intersects the sphere, it'll intersect it in a circle. And we can ask ourselves, well, what's a formula for, let's say, the circle's circumference, or the circle's area? Okay, so here's a problem we can try to solve. Find a formula for the circumference of a spherical circle of radius little r. Find a formula for the area of that same circle. So let's solve that problem. You can solve it fairly easily by using this result about the area between two planes by rotating the picture. Rotate the picture so that this plane becomes a vertical plane, say here, coming straight out of the board, so that my circle that I drew over there is in this position on the sphere. Okay, that's where the circle is. And if we wanted to find a formula for its circumference, well, the circumference of that circle is the same as the circumference of this circle, which is now vertical, coming straight out of the board. And if I call that angle theta, and I call this curved radius of the circle r, we know that that little r will be equal to capital R theta by some high school geometry. And if the radius of my big sphere is capital R, then that distance on my picture will be capital R sine theta. That distance here on my picture will be capital R cos theta. And the circumference of that circle on the sphere is the same as the circumference of the circle in a plane. It's an ordinary flat circle. The circumference is given by 2 pi times its flat radius, which is that distance there. The flat radius meaning the radius of that circle thought of as being a circle in the plane, not the curved radius that I called little r, the flat radius being the radius in that plane. The radius in that plane is capital R sine theta. So the circumference of that curved spherical circle is 2 pi r sine theta. Or I can write it as 2 pi capital R, and then theta I can solve from this equation. Theta is little radius over big radius. So that gives us a formula for the circumference of a spherical circle. And we can get a formula for the area by using this previous formula. So that disk is a slice of the sphere between those two planes. It's a slice on the sphere between two planes. And I can use that formula. Okay, 2 pi r delta x is the area. Delta x is the distance between those two planes in my picture, which will be capital R minus capital R cos theta. And I can bring out a copy of capital R to get 2 pi r squared, 1 minus cos theta. And again, I can rewrite theta as little r over big R. Okay, and so we've solved another little problem. We found formulas for the area and the circumference of a circle on the sphere. Here's another problem that we can solve, or another formula that we can obtain, which is quite a fun formula. We can find a formula for the area of a triangle on the sphere in terms of its internal angles. So when I say a triangle on the sphere, a triangle has 3 edges. The edges we call lines sometimes. A line on the sphere is a great circle. That's like an equatorial circle. It is a circle which you obtain by intersecting the sphere not with any plane, but a plane through the origin. If you intersect the sphere with a plane through the origin, you get a largest possible circle, like an equatorial circle. And in spherical geometry, we call that a line. And if you give yourself 3 lines, or 3 equatorial circles, okay, they will form a spherical triangle. And that spherical triangle will have 3 vertices, say UVW. It will have 3 angles, alpha, beta, gamma. The angles you can define precisely as angles between tangent lines, or you can describe them as being angles between planes, because each of these spherical lines is the intersection of a plane through the origin with the sphere. And if you take the angle between 2 planes, that'll give you the angle of the triangle. So a triangle's got 3 vertices, it's got 3 angles, it's got distances, which I could denote by, say, A, B, and C. It's got lengths, and you can study the geometry of a triangle on a sphere, a spherical triangle. So another thing that I'll get, another formula that we'll get, is we'll get a well-known formula for the area of this triangle in terms of its angles. So to find this area, what we'll do is we'll consider the area of a wedge like this. Consider the area of a wedge, an alpha wedge. Let's call that an alpha wedge. So we'll find the area of one alpha wedge. To find the area of one alpha wedge, it's convenient to rotate the picture so that that vertex is pointing directly towards you. And we can rotate the wedge so that one of the great circles is in that direction, horizontal, and the other one will be in another direction like so. Rotate the wedge so that it takes that form. And once you rotate it to that position, it's easy to work out what the area should be. Can anyone see what the area is from that picture? I'll write A sub alpha for the area of that alpha wedge. Can anyone see what the area of that alpha wedge should be? Probably someone can, but no one's got their hand up. So I'll write this one down. Let me start it off. It's alpha over pi times what? Times the full surface area. Okay, it's alpha over pi multiplied by the full surface area of the sphere, right, which you can see from that picture. And the pi's cancel, giving this formula for r squared alpha. So we've got a formula for one alpha wedge. To get a formula for the area of the triangle, we consider all three wedges. There's an alpha wedge, there's a beta wedge. Maybe I'll draw the picture again. Okay, so we've got a spherical triangle made up of three great circles, making three alphas, three angles, alpha, beta, gamma. Consider one alpha wedge, like so. One beta wedge, like so. And a gamma wedge, like so. And the alpha, beta, and gamma wedges that I've shaded, they cover the entire sphere, but they cover the triangle some extra times. So if you add them up, if you add up the area of the alpha wedge plus the area of the beta wedge plus the area of the gamma edge, what you get is the area of the entire sphere, which we know, plus a certain number of additional copies of the triangle. So a trick question, when I cover this, I like to ask the students a trick question. The trick question is, how many extra times does that triangle get covered by my shadings? And this is a trick question for people who haven't seen this before. 2 extra. So 2 extra is wrong answer. So it's a good trick question. It's a good trick question. 2 extra is the wrong answer. In my picture, it's covered 3 times by my 3 different shadings. That ought to be 2 extra times. Does someone know the actual answer? He's a geometer, so he knows. But so if you don't know this, it's not that easy to see, but there's actually 4 extra coverings of the area of the triangle because if I continue my picture on the back, which I can't do very well with my chalk, but you'll have to just imagine that it's continued on the back. If I continue the picture on the back, then there's an extra copy of the triangle on the back. It would be good maybe to have an actual sphere, maybe a ping pong ball with these lines drawn on it, and then you could see it clearly. There's actually an extra copy of that triangle on the back, an identical copy of the same shaped triangle with the same angles, and that triangle is also covered 2 extra times. So the triangle's covered an extra 4 times in total, and from here you get a formula for the area of the triangle. Right? We know the area of the alpha wedge and the beta wedge and the gamma wedge, so we solve this for the area of the triangle. It's 1/4 of the area of the total sphere, subtract the wedges, A alpha, A beta, A gamma. And just finishing off our formula, the area of the sphere is 4 pi capital R squared. And A alpha was 4r squared alpha. And A beta was 4r squared beta. A gamma was 4r squared gamma. And the 4's cancel, and we're left with r squared multiplied by pi minus the sum of the angles. And that's a very nice formula for the area of a triangle in terms of its angles. And it gives you one of the differences between spherical geometry and flat Euclidean geometry. In flat Euclidean geometry, the area of the sum of the 3 angles is always pi. The sum of the angles doesn't tell you anything about the size of the triangle. You can take your triangle and make it larger or smaller. But on a sphere, the 3 angles actually determine the area of the triangle completely. So that's another fairly easy thing that you can do if you want. I don't know how much time I have. 1 minute? 1 minute. I think I won't do the last topic because it would take me more than a minute. But I'll just mention something else that I often do. So I taught this topic last term in a linear algebra course. So the stuff that I did on the board today, you could easily do as an optional topic in, say, a calculus course when you're doing applications of integration. I did it in a linear algebra course, and you could do some more stuff, play around with some more ideas if you've done cross product. So if you've just taught cross product, maybe in a first linear algebra course, And if they've already done some calculus so you can do both, then you can play around with the cross product, and you can use the cross product to get a law of cosines. There's a law of cosines for spherical triangles. So if you give yourself a spherical triangle and call the vertices u, v, w, call the angles alpha, beta, gamma, the edge lengths, the side lengths a, b, and c, there's a law of cosines. There are actually two laws of cosines, but one of them gives you a law that says cosine of alpha is cos A minus cos B, cos C over sine B sine C, I think. I think that's the rule. And that rule allows you to solve for, say, angles given some lengths, like you can with a flat triangle. The ordinary law of cosines for a flat triangle allows you to calculate some angles given lengths, or sometimes it allows you to calculate some lengths given some angles. And you can use it in the same way, and you do it by using cross products. So you can make formulas for the sine and the cosine of this angle. You can make explicit formulas, okay, in terms of the other information by using cross products. So that's another fun application that I sometimes do, but I think I won't do it because it would take me at least 2 minutes.